related to the manufacturing and computer-aided engineering sector. 3 experiments will be presented as shown by the following agenda. So we start by this welcome introduction. Then the first presentation concerns the AI platform for automated training of object detection models based on CAD, done by Lucas Criete from Munoz. The second presentation concerns HPC-based multiphysics and multi-scale modeling of the autoclave process for aeronautical components. Pasquale Beni will present the main achievements and outcomes. Pasquale Beni is from Manta Group. The third presentation will concern multi-head additive manufacturing with optimal HPC thermal stabilization, and will be done by Nicola Blazevich from Micro Dvornica company. And we will end this presentation with some conclusions. Okay, I will let the floor now to Lucas for the first presentation.
Thank you, Sam, for the introduction. And yes, as introduced, my name is Lucas Criete. I'm CEO and co-founder of the company Munoz, who is a partner of the participating program. I'm happy to share our results for the FF4EuroHPC program. I was the project coordinator for the experiment IDECAT, which is the short name for AI platform for automated training of object detection models based on CAD data. Quite a long name, but I will explain what it has on it. And but I first want to introduce the field of application and the industrial case that we were working on. So the case that we were dealing with was the warehouse part identification for one of the partners' warehouse. The partner is Gabler Engineering, who is an SME who's producing manufacturing machines of pharmaceutical and medical products. And they have very specialized machinery, and therefore have their own designed parts that really deal for a special purpose. So there are a lot of variations and different versions for the part identification. So normally they have part numbers on them and or QR codes or barcodes. But since some parts are produced themselves, or like some parts get delivered by partners, it's often the case because they are quite special and not like norm or default parts. That is the case that some parts have no number on them, and the identification process can be quite exhausting. Therefore, the general purposes were to make it easier, cheaper, better. So like every company wants to do with their processes, quite general approaches. But for us, it means for the easier side, that the identification process has to be fast and simple to do. To make it cheaper, it is necessary to really generate a low manual effort. So to really deal with a system that there's no person to really has to handle the part number management, and that there's a high level of automation, and also data continuity, since there are a lot of different versions of objects or variations, as well as revisions that are made by the engineering team, should be directly implemented into the production as well as the warehouse process. So as a beginning for the project, we had some major requirements, which were with the goals that the AI object detection can output a list of part numbers. So there's a selection which is made by an AI. This is the approach that we chose. For the data continuity, these AI identification models always have to be up to date. This means revisions and different variations from the engineering has to be implemented directly into the identification models. And for the low manual effort, to generate the AI models, there's a high effort in the data labeling or taking images manually, and therefore this has to be reduced. So as hard facts or as hard requirements, the AI for our approach has to be able to identify 1,000 plus parts extremely fast. Then for the data continuity, since an update could be made, so like if the engineering is leaving the office, they can start the AI model generation process. And then the next day, if the production is starting to work, these updates should be implemented. So therefore, we set the goal to make overnight delivery for the AI models available, but as well as dependent on how many updates there will be made, that the AI model generation has to be as cheap as possible. So also small companies who don't have a high budget or like many changes that concur, that the AI model generation has to be as cheap as possible. And since there's a high manual effort in the data generation, that it has to be as fast as possible and at best automated completely. So in order to fulfill these requirements, we have built up a consortium of 4 companies, which were delivering or like working together on the whole process and regarding different aspects of the solution. So as introduced, we had Gabler, who were the main actor in the industrial case. So they would be the end user of the AI solution to reduce their search times and to improve their production processes. So they gave us the application and also the environment that we were performing our experiment in, as well as delivering all the data that we were using to generate the AI and also to validate our models. Then we have SolidLine, who is a reseller company for 3D modeling CAD software. And they were providing interfaces as well as supporting and consulting on how we can scale the business model so that the AI models based on CAD files could be implemented to multiple customers of theirs, but also would help in the sales process and defining the business model that could be scaled up. Then Kimono, which I'm directly part of as a domain expert in the AI process. So Kimono is specialized on delivering AI solutions, mainly with a service approach, and has done some research, but as well as developing solutions based on training with synthetic data, and is mainly specialized in the object detection process. Then for the computing side, we had the KIT, especially the Steinhoff Computer Center, which is providing the HPC center resources. So we performed every experiment on their computers, but they also were acting as an expert who were consulting and developing scalable and effective HPC processes and pipelines so that our approaches scale and can be distributed. So as visualization of the roles, we have here the pipeline that we developed. So it starts on the left with the CAD database from Gabler. Then based on interfaces and preparation of the data, we had SolidLine. Then the main process on converting CAD files into AI object detection models. We had Kimono. And for the parallelization process, we use the HPC from the KIT. And in the end, the detection itself, where the part identification process was taking place, Gabler was giving feedback on how the solution should look, that it could be implemented well in their process, as well gave feedback on how the solution should work and how good is good enough for them to really work effectively, and as well SolidLine, who were more looking on the business perspective on how the solution could be implemented in different systems. The general approach was a fast and easy detection for a large amount of parts, and the automated AI training on HPC. So in order to get this, we will have a look on our main requirements that I mentioned in the beginning of the presentation, and we will go a little bit deeper on what problems we had to solve. So let's start with the requirement that the AI has to be able to identify more than 1,000 parts extremely fast. So the main problem that we were solving with this was the manual part identification, where Gabler has some parts in the worst case that are not labeled directly or part numbers are missing. In best case, you can scan a QR code and everything's fine. But in the worst case, it gets quite exhausting very fast. So we are looking at the worst case where there's no part number or QR code or barcode on any of those parts. So it's not possible to automatically identify the part, and therefore the identification process has to be done manually. So the worker in really the worst case has to do it on paper, so he has to really like search folders. But also if he's doing it with a computer search engine, it's not that easy because he has to compare the part and the catalog manually. And this can take up a lot of time. So for one part, it easily takes up 5 to 10 minutes. And it's also not guaranteed that the identification process is correct. So that he really gets the correct number if there are similar parts and, for example, he doesn't find it in the beginning. And also, this is not like what the worker wants to do. He just wants to implement or take the right part or like place it somewhere where the part belongs if it's on its position false position. So the worker has a high level of frustration because he's not really doing what he wants to do. And therefore, the frustration of the worker is quite high. So what was our solution? We used the AI part identification to output a result quite fast. So the execution time of the AI in the end was less than 30 milliseconds. So we could perform a multiple detection process or identification process per second, and therefore ensure that there's not one false positive, since the detection is really fast and delivering results quite fast. The optimum case would be that the AI directly identifies the part, is 100% sure that the part number identified is correct, and therefore the worker only gets one number and he has the correct number. The worst case, we were writing up, for example, if some parts are very similar or just had some minor changes on a certain perspective, or just were different in scale, which can't be detected optically. We were outputting a list of 10 possible part numbers and requested an individual input from the worker, where we asked, can you show us another perspective, or can you give us like the weight of the object, or can you give us one side length? So he had to do one manual input, but then it was possible to identify the correct part number. And even with the individual input, we were able to reach an identification process that is less than 20 seconds. So on the second requirement we had was that we always want the data continuity, so up-to-date AI models. So we needed overnight and cheap AI model generation. So the problem in the beginning, when we started, it was quite not possible in the beginning. So if we wanted to update the AI identification models, in the first step, we had to implement those parts manually, and there was always manual effort on delivering or like integrating new objects or changed objects to the identification. So the manual, so it was the manual adding process that was quite a problem. So revisions and versions couldn't be added. And even then, if we were performing undistributed, so not in an HPC environment, we had long computing times, which were needed 100 hours plus. So therefore, only the computing times would make it impossible to do it overnight. And we had to do it on our own resources. As well as not every company, for example, Gabler, does not have the computing performance or resources that were needed to implement the or to train the AI. And therefore, for Gabler, it was not possible to implement it in their daily process. So our solution was to use distributed computing in an HPC environment. So we were able to parallelize the generation of the AI. So, for example, we were able to scale up for 1,000 parts to do the calculation on 1,000 nodes in parallel. So one node per part. Then the data generation and labeling process automated took less than 10 minutes if we do it in a distributed way. And the AI training itself took around 15 hours. So our requirements to do it on overnight, if the engineering is not leaving too late and the production is starting too early, this would fit in the overnight generation of the AI. And the cost level were like, if we were so the complete node hours, so 10 minutes like for 1,000 nodes would be 100 hours and 15 hours for the AI training. With €3 per node hour, one run for the whole data set would cost around €350. And therefore, if we are talking about multi-million dollar machines, or multi-million euros machines, €350 would not be that much, especially if we say we don't want to do it every night, but only, for example, delivering the updated model if there's a new machinery ready for production. And therefore, we developed a service approach where the training as a service became possible. Therefore, there's one service client running and is waiting on us to publish a new data that should be used for the training. And therefore, training as a service approach became possible. And therefore, revisions or different versions could be just uploaded through our environment. And therefore, the AI models would be updated directly. So for the last part was like the high manual or the low manual effort that we wanted to achieve. We had like the fast data generation and labeling. The main problem is that doing it manually, so taking real world images and then annotating those images by telling the computer what he sees, the effort would be extremely high. So we estimated if we have like one object, we would take an image of the object, and then we are telling the computer what he's seeing on this image. For example, we have like this kind of front plate. It would need 30 seconds on average to take the image, to name it, and to save it. And then we said at least 100 images are necessary. And for those 1,000 parts that were aiming at, it would need 833 hours. So one person working a 40-hour week would need 5 months to prepare the data sets for the AI training. So the effort for the data generation was extremely high. And our approach was to use synthetic images. So we rendered the CAD models, so the 3D models, and we're completely using a synthetic database. So it would not be necessary to even take one real-world image, and therefore the whole process could be automated completely. So there was absolutely no manual effort after the uploading process or like the publishing of changes. The whole process were running without any human who had to do or perform any steps. And as well, for the manual data generation process, we had like 100 images for 1,000 parts. We had a database of 100,000 images. We were able, because it was automated, to generate a lot or ways larger data sets. So, for example, in those 10 minutes, we were generating more than 20 million images, which were representing different scenes, different perspectives, and a very high quality data set. So there are no manual or human flaws in the data set. Main outcome, if we summarize our 3 requirements, that the AI must be able to detect 1,000 parts, that the AI model generation should be possible overnight and should be as cheap as possible, and that the data generation labeling should be automated. In the beginning of the experiment, it could take up 5 minutes plus for the manual search for those different parts, and we had a high level of frustration at the workers. The overnight and cheap model generation was quite not possible because there was always manual effort required, and we had the manual data generation, which took 800 hours plus. So as a result, the automatic identification for those 1,000 parts was possible in less than 20 seconds. The automatic training was overnight possible and for less than 350 euros. And there was absolutely no more manual effort in the data generation, and the process was able in less than 10 minutes. So the business impact is detection models can be offered a lot cheaper. AI applications can be delivered a lot faster. The search times at the warehouse were reduced drastically. The workers felt supported and can focus on their more productive work and less of searching parts that resulted in high frustration. The training became possible as a service, and therefore we have as a service which makes it possible to provide software as a service, and therefore has a high availability for different companies with all the necessary resources in the back end, and also offers a quite scalable business model with high annual recurring revenues. And therefore, Kimono, who is providing the services, is able to expand their business, since the effort is not growing with different customers, since there's no manual effort necessary. Thousands of customers can be served at once with resources on demand. So the next steps are we are aiming to integrate those services in a cloud platform structure so that every company is able to use it, as well as the integration in the whole process at Gabler's, and as well as in the infrastructure. So overall, we are quite happy with our results and think we achieved major improvements of the whole process, and are now aiming to scale up the solution and make it business ready to make our service approach available for as many companies as possible.
Okay, good morning to everyone. I'm Pasquale Bene, and I'm structural engineering, and I'm part of CHETMA Research Center, and I'm part of the numerical simulation area of the CHETMA. Today I will talk you about the MULCOM experiment concerning the multiphysics and multiscale modeling of the aeronautical components. The partner involved in the experiment are Manta Group, that is the coordinator and then the user of the experiment. Manta is a small company that operates in the aeronautical field, producing composite parts of aircraft, and it is one of the strategic supplier of Leonardo SPA. Cineca is the HPC center, and CHETMA is a private research center which is specialized in composite material sector and the advanced simulation techniques. The problem regards the autoclave molding process, which is the main fabrication method for composite parts using the aerospace sector. This process involves both mechanical and chemical phenomena, and a very number of variables affect the final results. So the setup of the process parameters is very difficult, and usually an expensive trial and error approach used for the production of complex shape components. And as a consequence, the quality of the composite parts and the production volume are very low. The goal of the experiment is to optimize the autoclave process parameter and the composite material performance in order to reduce the time to market, to enhance the parts quality, to reduce the design cost and the material waste, to increase the production volume. The approach proposed and used in the experiment is based on a multi-physics and multi-scale numerical model able to study the influence of the thermomechanical phenomena that are involved in the autoclave process on the macromechanical performance of the composite parts, but also the effect on the microstructure of the composite material to predict the defect formation and how they affect the final properties of composite parts. These analyses are based on a multi-target optimization criteria in order to consider the interaction between the process parameter and how they affect the defect presence and the mechanical performances of the final component. To do this, HPC resources are required to reduce the computational time and to set the manufacturing process in a quasi real time. The work plan of experiment consists of 4 tasks. In task 1, the key results are the collection of all inputs needed to set up the numerical model and the outputs to be monitored in the numerical simulation. In the task 2, the key results are the setup of 2 numerical models, a thermomechanical model on macro scale to predict the dimensional change of composite parts during the autoclave process due to residual stress, and a fluid structure model on micro scale to investigate the pressure effect on the resin flow and the void content in the composite parts that affect the mechanical performance. In the task 3, the key results are the access to the HPC resources of Cineca and the definition and validation of all procedures to be used the HPC resources. And finally, in the task 4, the key results are the development of and the manufacturing of a full-scale prototype in composite material and the benchmark test using HPC system in order to investigate the scalability of the finite element codes and therefore the computational time reduction. In particular, in the task 1, the results are the selection of a critical component to be manufactured by autoclave process and the composite material to be used, the operating process parameter and the output to be monitored in the numerical simulation, such as stress and deformation level of component, resin pressure effect, and porosity content. In task 2, experimental test on sample geometry have been carried out to have data to be compared with the numerical analysis results. The aim was to calibrate the numerical model in order to fit the experimental results. 2 sample geometry are used, flat part and angle part. This slide shows the composite parts after the curing process and the measurements of dimensional changes. Ultrasonic inspections have also carried out on the cured parts to investigate the presence of defects such as voids, inclusion, delamination, or porosity, and consequently the effectiveness of the autoclave process. The results of the experimental test show that the parts are acceptable and comply with the technical requirements. Therefore, the autoclave cycle is suitable and no further refinements are necessary. This video shows the numerical simulation of the dimensional change of a flat laminate during the autoclave process. During curing, the composite parts undergoes chemical physical transformation that increase its strength and mechanical properties. But the composite parts is in contact with the metal mold, which has different thermal and mechanical properties. This induce residual stress on the composite laminate that results in undesirable dimensional change during the molding. The geometric distortion after curing are of about 0.5 mm, which are agree with the experimental test results on sample geometry. The same analysis have been carried out on the angle laminate in order to calculate the spring-in effect, which is the angle variation produced by residual stress during the curing process. In this case, the angle change is about 2.4 degrees, which is in agreement with the experimental test obtained on the angle part. Delaminate compaction due to resin flow is another important cause of geometric and dimensional unconformities. To simulate the pressure effect, a fluid structure model on a microscale level was implemented. In the preliminary analysis, only one composite layer had been considered in order to simplify the setup of the numerical parameters. In the next analysis, the effect of the pressure for all plies involved in the composite layup have been considered, and the HPC resources have been used to reduce the computational times that otherwise would be very high using a normal workstation. A numerical sensitivity with different levels of pressure is carried out, and the best pressure value obtained is of 6 bar, which allow an acceptable compromise among the integrity of toe, the level of voids, the compaction of fabric layer, and the mechanical behavior of the final material. Okay, once the macro-mechanical numerical model was validated by means the comparison between numerical and experimental results on simple geometries, this model has been used to develop a full-scale prototype. The component identified is a critical part of the Manta Group production and concern a rib of the elevator, which is a component of the empennage of aircraft. In this slide are reported the CAD model and the finite element model used in the numerical analysis. In the first analysis, the preliminary layup has been used to investigate the geometric distortion of the geometry due to residual stress. The layup consists of 6 layers, which are a bidirectional fabric with the fiber both in the 0 degree and 90 degree direction. After the molding, the maximum geometric distortion of part is about 1 mm, and consequently the part is not acceptable. Therefore, a layup optimization by numerical simulation have been carried out in order to reduce the geometric distortion. Thanks to the collaboration of Manta groups and its experience on the production of composite parts, a best fit of the layup was identified. Different types of composite layer are used: fabric and tape layers with carbon fiber, but also layers with fiberglass. This slide shows the final layup of the rib, able to meet the production requirements. In this slide are reported the contour plot of the displacement of rib after the molding. The maximum geometric distortion of part is about 0.2 mm. The composite part satisfies the geometric and dimensional tolerance, and consequently the part is acceptable. Next step concerning the prototypes manufacturing by using the optimized layup resulting by the numerical analysis. This slide shows the production step, the layer deposition, the value bag application, the curing process in the autoclave, and the trimming by CNC machine after curing. Then the dimensional check of parts is carried out in order to verify if the geometries meet the requirements. From the results obtained, it is evident that all prototypes satisfy the requirements, and consequently the parts are acceptable. Benchmark tests are carried out in order to investigate the scalability of the finite element codes and to calculate the reduction of the computational time than the workstation available by CHETMA. Exploiting all licenses available, the workflow time is lower than 1 hour, and the computational time reduction using HPC system is about 63%, with the implicit code used for the thermomechanical analysis of the curing process on macro scale. The same tests are carried out with the implicit code used for the fluid structure analysis on microscale. In this case, considering the same course number, the computational time reduction using the HPC system is about 80%, while using 480 cores, the workflow time is lower than 15 minutes. Regarding the business benefits by using HPC resources and advanced simulation techniques, Manta expect to reduce design cost by 50%, material waste by 70%, and raw material usage by 15%. CHETMA will be able to exploit the outcomes of Malcolm, offering the knowledge acquired in a new research project and consultancy services to other SME. Cineca aims to become Manta provider of HPC resources and to exploit the outcomes of Mulcom to attract new customers. The benefits of the other benefits are the creation of a partnership among Manta Group, CHETMA and Cineca for the exploitation of the experimental results and future collaboration. They enabled access to advanced HPC platform, improve the visibility and the new networking opportunity, and acquired the new knowledge on the curing process of composite material to be used in new research projects and consultancy service.
Thank you, Pasquale.
Hi, everybody. I'm Nikola Blažić. I'm the CEO of the company Mikrotvornica on Croatian. It's pronounced on English Microfactory. So the project that we conducted as an experiment is a multi-head additive manufacturing with optimal HPC thermal stabilization. The experiment consortium was consists of Mikrotvornica as an end user and Roger Bošković Institute as an HPC expert and simulation support. We had during the project we had also one new partner, Red Fluid Dynamics, that helped us implement open source solution for conducting the simulations and developing the complex model that I will tell you more about. Okay, what was our challenge? What we wanted to test during this experiment? The main thing in industrial machines for 3D printing, especially FDM or FF technology, is that the heat and its dissipation inside the machine and on individual structures, elements of the machine play one of the major roles. So heated workspace inside the printer is something that is needed to be when you are using 3D printing for industrial materials. So it's needed inside the machine, but it is something that can cause problems for the final product, you know, because the machine is using the temperature, and it can be a problem for measurements of the 3D printed part as the end product. So what we wanted to do is to optimize the production and the assembly of the machine by conducting simulations before the actual assembly of machine itself. So the solution that we wanted to use is we need to establish and predict the impact of this heat inside the machine on the structural elements. We wanted to predict how the propagation of the temperature inside the machine is doing through several checks within simulation using HPC. Why we needed HPC? Because model of the 3D printer and the propagation of the heat and inside it is something that is a complex situation and needed to be done on the models that when you are using a standard equipment like computers, not an HPC solution, it can be like 15+ days for one simulation. So it's not something that it can be done on a normal computer. So HPC here was the proper solution. So I will move on to the next. Now I will talk something about technical stuff that we used during the experiment. So the experiment was conducted in 5 phases. The first phase was that we needed to finish and develop 3D model assembly, digital assembly of the machine. it is something that we later, you will see in phase 4, used for constructing the actual machine to order physical parts and everything. So this is a model for CAD model for that is a base for performing and using a model for simulation, and it is a base that we used for physical parts. So the first phase of the project was the conduct and finish the digital assembly of the machine. On these pictures you can see on the right is the actual finished digital assembly of the whole machine. On the in the center is structural elements, the whole linear rails of the whole machine, and the left picture is outer shell that is consists of plastic and mostly metal aluminium parts. So in the second phase, when we finished our 3D model, we moved on to using simulation. The first phase was okay. We needed to conduct basic simulation of the linear rail as a main structural element of the machine. I needed to put out that within the project we had a major switch to in a software solution because we wanted to scale as much as possible on HPC, and first solution was ANSYS, but when we wanted to go like on a HPC scale, the solution needed to be transferred to an open phone because of the costs and everything of scaling on ANSYS, and we moved to an open phone because we can scale as much as we can, but because we didn't have an experience with an open phone there, then we got a new partner that helped us develop the model and so on. It was a successful partnership. So I will go on the phase 3. In the phase 3, we conducted first we conducted the simplification of the 3D model. As you can see on the left, it's a actual machine, and on the right is a simplified model that you can see in the different colors and everything, the main parts that we needed to test during the simulation, the outer shell, the main profiles, that is something that is important for actual 3D printing, and 3D printed heads are in the blue, and the red is the main source of the heat and heated element. It's the heated bed. It's used in this industry when you are actually printing the parts. You will see later one picture of our test. Starting from the original geometry, simplified one was created. So that was the first thing in the phase 3 to have a simplified model that we will be using for simulations. Here you can see what are the elements. As I already told you, you have a hot plate, rails and print heads, interface cabinet, and so on with its physical properties. Okay, this is the one of the older videos, first videos of the simulation that we have. I have also a new ones, but unfortunately something wasn't working to put it in this presentation. But you can see here the first iterations of our model that we used, and how the propagation of the temperature inside the machine is iterating. Okay, the later videos that we have are more complex, and we tried to compare it with the actual physical results. So in the phase 4 of the project, we conducted the phase 4 during also the phase 3, but it's a totally different job. You know, in the phase 3 we are using simulation. We are working on a computer and everything, but phase 4 is something more doing with your hands. You know, as you can see, here is the actual machine. I don't know, can you grasp the size of it? It's like 1.8 meters in height, so it's a pretty big machine. We conducted the whole assembly of it, and we put here is the little box and the sensors inside on the different places to measure the temperatures inside and how it's propagating in the whole environment inside of it. So the phase 4 was a physical thing, you know, assemble the machine, actual machine. So when we had the machine finished, and we have like simulations, first simulation of propagation of temperature inside, we then started to test and to compare the results. One of the first things was we are measuring temperatures inside. You can see the picture. This is only start of the heating cycle. The temperature inside can be measured, I think, like 50 to 55 Celsius during the 1 or 1.5 hour of heating. You know, that's the physical, actual physical measurements, and we have some differences with simulations, and we tried to be as precise as we can, but we have some differences in the timeline. You know, the simulations were like 30 to 50%. I think it's around that numbers. It heated up quicker than the physical machine, but that's something that in the first experiment using like this, it was really good result, because we have actual propagation really similar with the actual testing. What results, technical results, can help us with this when we want to upgrade our machine for better results, like we can move it. What we need to do with the machine if you want to have like the whole machine heated up in 30 minutes, so we can use our simulation to put isolation inside of it, different tools, different materials. We can test it on the actual simulation. We don't need to construct another machine. It's always that is always really expensive. If you do something wrong, okay, it's not something that you can fix it like with a few clicks, like on a computer. So it's always better to have as much as precise results. The second phase of the testing was actual 3D printing. So the results that we wanted to see is how can we make our machine more precise. So we measured, we conducted the tests in different situations, like on an open machine, closed machine, on this temperature, and what's going on with the 3D printed parts. So we conducted also a few cycles of measurements in 3D printed parts, and we even needed to make different types of measurements during the project, but because we saw that we have differences, it was like, okay, our hypothesis was the part will be slightly bigger, but it was slightly smaller. What's going now? You know, it's something you are like doing experiment and all your hypothesis is different. And we then concluded that we measured not in a proper way. We needed to measure it in different cycles. Okay, that's something that is not easier to explain here, but we managed to grasp what is our fault, and we then did it conducting second tests, and then we proved our hypothesis. Okay. The main physical exploitable outputs, we developed a really complex model for performing simulation. That's something that is really important for us, because we can use that for conducting experiments on the actual product that we have, and if we want to go further in the HT filaments and everything, we can use this simulation to have more and more better results that we use before construction of the new machine. Okay. Better understanding of using open source solutions. That was something that just popped up, you know, during the experiment, because we needed to move to an open source solution, and we gain knowledge in doing this kind of stuff with the OpenPhone. That is something that is also good for us, you know. Valuable data from measurements of 3D printed samples. We used a few of tests, but we wanted to expand our database throughout the whole range of materials that we can use on this kind of machines. The last thing, of course, and the important thing about business impact and benefits for us, what's the always something that you need to have if you want to be competitive of the market, is how to lower your price for your customers and be quicker. You know, the first thing that we saw is that we can possible shortening of delivery time of 30 to 50%, because if you have results, proper results that we know are good within our simulation, the first calibration of the machine when you want to finish it and for your customer, we can use it in a short amount of time, because we have a database and data from the simulations. Of course, if something is shortening the time of human labor, then you can cut costs in production by 50 to 30%. These are all estimates. We need to like do it on the 10, 15 machines to be the precise as possible, but these are really good estimates. Greater accuracy of the 3D printers can achieve increase in sales. That is something that is, if you want to be on the really competitive market of industrial machines for 3D printing, accuracy is everything. So that's something that we can, data from simulations and testing, we can use it to better and quicker calibrate the whole process. So it can be the part that you can produce inside the machine can be of greater accuracy, of course. Importance of gaining knowledge in using simulation with HPC. This is our first touch with the HPC infrastructure, and if we can gain results in like 3 to 4 days, and have something that you can use for your product, it's really something different, you know. So definitely something that is really good for us. And of course, that was pretty important for me, you know. I wanted to see is using HPC in this manner, like is it better to invest in that kind of equipment in the company, or use it like something from outside? And it was no brainer, because 62% is cheaper for us, for our business model. It's cheaper get HPC from the outside and not to use it inside it or invest in that kind of equipment. But I needed to have like numbers, yeah. And here is the full picture of the machine and the team of the people that worked on this. Also our mascot Guinea, as you can see here on the picture, yeah. The thing that is the most important also for us is the opportunity that was given to us to use HPC resources, and we see definitely then we can speed up our efforts to design and construct these kind of machines. And we hope that in the future we will use it as much as possible. So thank you all. That was all of me.